This is Sirichandra from CSCF, roll number 24951A05BN. Today I am going to talk about monoclinic lattice. The introduction to monoclinic lattice. The monoclinic lattice is one of the 7 crystal systems in crystallography. It is categorized by 3 unequal axes with one of the angles being 90 degrees. This lattice type is commonly found in minerals and certain mineral structures. Crystal system overview. The monoclinic system is distinguished from other crystal systems by its unique axis arrangement. It includes a single axis that is inclined relative to the other two axes. This results in a distinctive geometric shape and symmetric properties. Axes and angles. In a monoclinic lattice, two axes are perpendicular while the third is inclined. The angles between the axes are denoted by alpha, beta, and gamma. Typically, alpha and gamma are 90 degrees, while beta is greater than or less than 90 degrees. Let's learn more about characteristics of monoclinic lattice. Unit cell parameters are lengths and angles. The 3 edges of the unit cell are unequal in length. Lattice parameters. The lattice parameters define the length of the axis and the angles between them. For monoclinic lattices, the parameters are denoted as A, B, C, and beta. The parameters help determine the unit cell dimensions and crystal symmetry. Next, we'll learn about unit cell structure. The unit cell is the smallest repeating unit that reflects the crystal's symmetry. In a monoclinic lattice, the unit cell is typically a parallelogram prism. This structure influences the physical and chemical properties of the crystal. Symmetry elements. Symmetry elements in the monoclinic lattice include rotation and mirror planes. The monoclinic system generally has one two-fold rotation axis. Such symmetry contributes to the classification of the crystal's properties. Types of monoclinic lattices. There are 2 types of monoclinic lattices, the C-centered and the base-centered. C-centered lattices have lattice points at the center of the unit cell, while base-centered do not. These variations can affect the crystal efficiency and density and packing efficiency. Examples of monoclinic crystals. Common examples of monoclinic crystals include gypsum and orthoclase. These minerals exhibit the unique properties of the monoclinic system. Their applications in geology and materials science are significant. The shape. The unit cell resembles a disordered rectangular prism where one pair of opposite faces is tilted relative to the others. Symmetry. The monoclinic system has a low level of symmetry compared to cubic or hexagonal systems. It allows the one-fold rotation axis or one mirror plane. Types of monoclinic lattices. There are 2 types of monoclinic lattices, primitive and centered. The lattice points are located only at the centers of the cell of unit cell are called primitive. Centered. The lattice points are located at the corners and in the center of one pair of opposite faces. More examples of monoclinic crystals are monoclinic sulfur and muscovite. Applications. Understanding monoclinic lattices is important in fields such as mineralogy to classify and study materials. Minerals. Next is material science to analyze the properties of materials with monoclinic structures. And next is pharmaceuticals. Many organic compounds crystallize in monoclinic systems affecting solubility and stability. Crystal growth. Crystal growth is monoclinic structure can be influenced by environmental conditions. Temperature and pressure play crucial roles in determining crystal morphology. Understanding these factors is essential for synthesizing monoclinic materials. Next is physical properties. Monoclinic crystals exhibit unique optical and mechanical properties. These properties can include birefringence due to their anisotropic nature. Such characteristics are vital for applications in optics and material engineering. Next is X-ray diffraction. X-ray diffraction is a key technique used to study monoclinic crystals. It helps determine the arrangement of atoms within the monoclinic lattice. This method is fundamental in characterizing material structures. Applications in material source science. Monoclinic lattices are important in the field of material science. They can be found in ceramics, semiconductors, and phosphors. Understanding monoclinic structures enables advancements in material design. Next is comparison with other lattices. The monoclinic lattice can be compared to orthorhombic and triclinic lattices. Unlike orthorhombic, monoclinic systems have one angle that is not 90 degrees. This distinction influences the crystal symmetry and physical properties. Next is computational modeling. Computational methods are often employed to simulate monoclinic structures. These models can predict properties and behavior under various conditions. Accurate modeling helps in the design of new monoclinic materials. Uh, Monoclinic lattice in biology. Monoclinic lattices are also observed in biological systems such as proteins. The arrangement of amino acids can lead to monoclinic crystalline study. These lattices, crystalline structures. Studying these lattices can provide insights to biological function. Let's learn more about geometrical properties of monoclinic lattices. Unit cell dimensions. A monoclinic cell has three unequal edge lengths A, B, and C. Lattice points. Lattice points in the monoclinic system represent positions of atoms, molecules, or ions. These points repeat periodically to fill three-dimensional space. Symmetry or monoclinic lattice. Low symmetry. The monoclinic system has less symmetry compared to other crystal systems like cubic or hexagonal. Symmetry elements. One two-fold rotational axis and a possible mirror plane. Types of monoclinic Bravais lattices. There are two Bravais lattices in the monoclinic system. Primitive monoclinic. Lattice points only at the eight corners of the unit cell. And next is simplest type of monoclinic lattice. And the next is base-centered monoclinic. Lattice points at the eight corners and the eight at the centers of two opposite faces. Adds additional symmetry compared to primitive lattice. The organic molecules like urea crystallize in monoclinic systems. Next is challenges in study. Studying monoclinic lattices presents unique challenges due to their complexity. The variability in lattice parameters can make characterization difficult. Advanced techniques and technologies are required for detailed analysis. Future research directions. Ongoing research is focused on the synthesis of new monoclinic materials. Investigating the properties can lead to innovative applications. The potential for discovering new monoclinic compounds remains high. Next is notable research studies. Several studies have highlighted the significance of monoclinic lattices in technology. Research on monoclinic materials has implications in electronics and photonics. Notable findings continue to emerge in the field of crystallography. Next is summary of these points. The monoclinic lattice is a vital structure in crystallography with unique properties. Its applications span various fields including materials, science and biology. Understanding this lattice type is crucial for advancements in multiple disciplines. Conclusion is monoclinic lattice remains in an important area of study in crystallography. Future advancements will likely reveal more about its properties and applications. Continued research and exploration are essential for unlocking its full potential. This presentation format provides a comprehensive view of the monoclinic lattice, its characteristics, examples, and significance in monoclinic lattice. Thank you.